Contemporary thinkers have invented purely artificial geometries to predict and measure imaginary mathematical worlds. These geometries of space were born from puzzles about our physical universe that engaged the ancient Greeks nearly 3,000 years ago. Armed with a profound sense of mathematical exploration and a deep grasp of the fundamental tenets of geometry, they made remarkably accurate deductive measurements, calculating the distances to other planets and remote distances on the surface of the Earth. Sometime around 300 BC, Euclid compiled geometric laws and proofs in a book he called The Elements. Containing what we think of today as Euclidean geometry, it provides the mathematical techniques used by ancient mathematicians and modern ones to measure spatial relationships. One of the most basic shapes used in making measurements is the triangle. Even before Euclid formalized geometry, mathematicians were busy applying the special properties of triangles to problems of measurement. In the 6th century BC, a Greek mathematician named Thales made several important calculations. Thales is credited as the first person to calculate the distance of ships at sea. He did it using the concept of congruent triangles. Two triangles are said to be congruent if one is an exact copy of the other. In other words, if their corresponding angles and sides are equal. I decided to reenact Thales' method on the bank of the Charles River in Boston. First, I stood at this point directly opposite the ship. Let's call it A. And let's call the place where the ship is B. Then I walked a certain distance along the bank on a line perpendicular to AB. I stopped and planted a stake S. Now I walked the same distance again, planting another stake. I made a 90-degree turn at point C and walked away from the riverbank. I kept walking in a straight line until stake S and the boat at sea were directly lined up. Nope, not yet. When everything comes into alignment, the distance of the ship from point A will be the same as that from point C to where I ended, point D. Let's take a closer look at Thales' problem and solution with a simplified diagram. B is where the boat was, and A is where he first started walking. Thales planted the stake at S and kept walking to C. Then he turned at a right angle and ended at D, forming two triangles. First of all, we know that the angle at C and the angle at A are both right angles, because that's the way Thales set the problem up. We also know that these two angles at S are equal because opposite angles are equal. And we know that AS is the same length as SC because he paced off equal distances. Therefore, these two triangles are congruent. That means the distances DS and SB are the same. Hence, our distances BA and CD are the same. Perhaps the best-known mathematical theorem for finding the distance between 2 points is named for Pythagoras, a Greek mathematician of about 500 BC. Pythagoras was a mystic who combined his metaphysical interests with mathematics. To illustrate this theorem, let's look at a triangle with a right angle. Here's the base, and here's the adjacent side. The hypotenuse is the side opposite the right angle. In this case, let's say that the base is 3 inches long and the adjacent side is 4 inches long. The Pythagorean theorem says that the square of the base plus the square of the adjacent side will be equal to the square of the longest side, or hypotenuse. Here's how we figure out how long the hypotenuse is. The formula is a squared plus b squared equals c squared, remembering that b is the base, a is the adjacent side, and c is the hypotenuse. So if a equals 3 and b equals 4, then 3 squared plus 4 squared equals c squared, or 9 plus 16 equals c squared. Thus c squared equals 25 and c equals 5. The length of the hypotenuse, then, is 5. Historically, the Pythagorean theorem found its practical origins in ancient Egypt. The Egyptian scribes, sent out to measure parcels of earth in order to levy accurate taxes, used lines and triangles stretched out of rope to survey the land. The contemporary use of the Pythagorean theorem hasn't evolved much. It's still employed to make land measurements, but not always with taxation in mind. Charles Roselli, chairman of civil engineering at Boston's Wentworth Institute of Technology, teaches his surveying students the finer points of Pythagoras.
Okay, all right. What we're going to do today is lay out a small building. Oh, let's say a 30 by 40 building. How's that? That sounds good? Okay. 40 foot for the frontage, 30 for the depth. What do we use for the diagonal?
50.
50 feet. Okay, how did you get to 50 feet?
Pythagorean theorem.
Okay, the Pythagorean theorem, all right? Which would be your 30 squared plus your 40 squared.
These students are about to stake out 2 points 40 feet apart for the front face of the building. They'll use the Pythagorean theorem to make sure the sides of their building meet at right angles.
What you simply take the 50-foot mark, hold it on one of the corner points of the front of the building, take the 30-foot mark, hold that at the other corner point, and simply swing the 2 tapes together until the 2 zero-ins come together. That'll give you the 3rd corner.
They can get the 4th corner by repeating the process. This method is foolproof for laying out a building with squared corners. As we'll see again when we tackle more complicated problems, the ability to lay out a right angle turns out to be an important geometric tool. Another useful geometric idea employed in measurement is that of similar right triangles. This concept differs from congruent triangles in that corresponding sides of similar right triangles don't have to be the same length. By this time, the notion of similarity is not a new one for us. Remember that 2 triangles are said to be similar if their corresponding angles are the same, even if the lengths of their sides are different. Informally, 2 triangles are similar if one is an enlargement of the other. Thales knew that if right triangles were similar, then their sides would be proportional. So armed with this geometric knowledge, Thales set out to measure the height of the pyramids. At the site of a pyramid, he held a stick upright on the ground and measured its height and the length of its shadow. The right triangle, whose legs are the height of the stick and the length of its shadow, is similar to the right triangle, whose legs are the height of the pyramid and the length of its shadow. So for any point in time, the ratio of the 2 heights, pyramid over stick, is the same as the ratio of the lengths of their shadows. Thales' stick was 10 feet long and cast a 16-foot shadow. When he measured the shadow of the Great Pyramid, he found it to be 770 feet. From this equation, Thales saw that the length of the pyramid's shadow was 48.1 times the length of the stick's shadow. All he had to do now was multiply the length of the stick by the magnification factor. 10 times 48.1 equals 481 feet, the height of the pyramid. Well, it turns out that this concept of similar right triangles is really a mathematical light at the end of an engineering tunnel, figuratively and literally. You see, the modern use of right triangles in engineering projects depends on the same principle of similarity. For example, suppose that you really want to build a tunnel, like this one in the Boston subway system. First, you have to decide which direction to dig. Once underground, it's difficult to keep your bearings. How do you decide which direction to dig without coming up to the surface to check if you're heading the right way? In Pythagoras' hometown, a mile-long tunnel was built on the Greek island of Samos to bring water under a mountain into the city. Latter-day historians were impressed to see that the tunnel was built without any vertical shafts that the builders could use to come to the surface and check their direction. Here's how they probably did it. Suppose tunnel entrances are to be at A and B on opposite sides of the mountain. Let's mark off an arbitrary distance from B, like 750 meters, and call that point E. We'll make a right turn at E and go 1,000 meters to F. Then at F, we'll turn right again and go 2,000 meters to G. We'll turn right once more and walk straight. From A, we erect a perpendicular, hitting our path at point H. So then we measure GH and AH. we find GH equals 800 meters and AH equals 250 meters. Now, we have to draw an imaginary right triangle with the hypotenuse AB and the right angle on the line EB. Let's call the point where the right angle occurs C. By subtraction, we know that AC equals 200 meters and BC equals 1,000 meters. Any right triangle with legs in the same ratio, 5 to 1, will be similar to triangle ABC, and its angles will be equal to those of ABC. So, to find the direction to dig, let's pace off two triangles. In triangle BOP, make the length of BO equal to 50 meters and OP equal to 10 meters. Angle OBP equals angle CBA. The second triangle, AQR, is identical to triangle BOP. The angle RAQ, then, is the same as angle OBP, which equals angle CBA. Consequently, points P, B, A, and R all lie on the same straight line, and that's the direction along which we dig. That was pretty complicated, which is all the more reason to admire the ancient Greeks for coming up with it. In fact, the method used in Samos was so precise that tunnels are built in much the same way today. Metropolitan Boston recently completed an extension of its Red Line subway system. Tunnel designers used the same concept of similar right triangles that we've been talking about.
The actual layout used in tunnel building, the mathematics of it, really are not much more sophisticated than you would learn in high school math class. The basics of trigonometry and geometry, some algebra combined with the principles of surveying, some engineering formulas, and once again the use of new type survey equipment really enhance and make the tunnel building very much the same as it was done centuries ago.
But project engineers like Peter McNulty, unlike the ancient Greeks, plan to do their digging under the commercial and residential areas of a modern city.
To do that, we'd like to stay in an open space, and the only open space in those areas are city streets, essentially. Obviously, that's not possible for the entire route. And when we proceed under structures, houses, businesses, certain considerations have to be made to minimize the impact on those areas, such as we try to keep the tunnel as deep as possible as we passed under those residences.
Although the techniques used to survey this 3-mile subway network were identical to those used by the Greeks, contemporary tunnel builders have the advantage of high-tech instrumentation.
You can actually send out an infrared beam of light and have it bounce back and give you an exact reading of how many feet to the nearest thousandths of a foot that the light has traveled. That has just increased the speed and accuracy of the surveying techniques dramatically. As we traverse from the Harvard Square station area out to the Porter Square station area, for instance, we found that we were very close, perhaps within 3 inches of our desired goal. That 3-inch deviation being more attributable to the construction methods than the actual surveying. The surveying was within several hundredths of a foot.
Numerically computing angles and measuring distances caused problems for the ancient science of geometry. You see, by its very nature, geometry often required drawing complicated diagrams plotted to scale in order to make measurements. The desire to simplify the process led to the development of trigonometry, a branch of geometry devoted to measuring triangles. Trigonometry revolves around the basic notion that the ratios of corresponding sides of similar triangles are the same. If we think back to the way that Thales measured the height of the pyramid using the height of a nearby stick and its shadow, we can understand just how useful trigonometry is. In trigonometric terms, when we want to determine the height of an object, the ratio we're using is the height of the stick over the length of its shadow, or side A over side B. This ratio is called the tangent of angle A. The tangent for angles between 0 and 90 degrees is the ratio of the side opposite the angle to the base of the triangle. Two of Thales' successors realized the intrinsic mathematical importance of his stick-to-shadow ratio. They expanded on Thales' work and went on to develop a chart of trigonometric functions which gives the ratio of sides in any right triangle for angles from 0 to 90 degrees. There are 3 pairs of sides, and therefore 3 ratios and their inverses are possible in every right triangle. When this chart is available, the heights of inaccessible objects can be measured without the use of a stick. The object's own shadow is the base, and the tangent allows us to calculate the object's height. If the sun is 30 degrees above the horizon, the tangent ratio is 0.5774. This would result in the stick shadow being longer than the stick itself. If the angle of the sun is 45 degrees, or halfway up the sky, the ratio is 1. This means that the length of the stick and the length of its shadow are the same. If the sun goes higher, to 89 degrees, or almost directly overhead, the ratio is 57.29. In this case, the height of the stick would be much longer than its shadow. In fact, 57 times the length of its shadow. Modern-day surveyors don't use sticks and shadows to make their calculations when measuring heights or widths, but they do employ the same trigonometric ratios. With a surveying instrument like the Transit, a modern surveyor can set up similar right triangles without being dependent on the sun. To calculate the height of this building, Wentworth Institute surveying students have placed the Transit at a convenient horizontal distance from the building. First, the ground distance between the tripod and the building is measured.
Good, Marv?
Good.
All right, distance to the building is 95 feet 7 inches.
Okay.
The Transit is pivoted and a sight is made at the top of the building. The angle formed by the Transit before and after the pivot, the distance to the top of the building, C, the horizontal distance to the building, B, and the unknown height of the building, A, form a right triangle. The angle is measured using the Transit.
Okay, the angle is 33 degrees, 8 minutes, 0 seconds.
Okay, got it.
The tangent of this angle, or A over B, gives the height of the building above the Transit. All that's left to do is add the height of the tripod to our figure.
Jim, the height of the building was 66.6 feet.
Good. When you look at the methods that are used today compared to what would be used centuries ago, you probably could best see it in Raiders of the Lost Ark, a contemporary movie. If you recall, at that point, they had a staff, and when they were trying to locate, I believe it was in the treasure room, as I recall it, they had to have the staff at a certain height, certain position, and what they relied on was the sun casting a shadow from the staff. And this is similar triangles. It's exactly the same type of principles we work with today. It's a proportional type thing. At a certain height, the shadow will go a certain horizontal distance. What we did today is we worked with a horizontal distance and calculated the height, just the reverse, but the same exact principles. More precision, more detail, but nothing has really changed.
2 other trigonometric ratios are known as sine and cosine. They're like tangents, except that they're the ratios of different sides. Remember, the tangent of angle A was the ratio of A over B. Identifying our new ratios, the sine of angle A is A over C, and the cosine of A is B over C. Which ratio you use depends on which sides of the right triangle you already know and which one you're looking for. Commonly, in finding heights, you're looking for the length of side A and therefore using the tangent of angle A. Trigonometry was the spark that ignited a rush of spectacular measurements. About 200 BC, a Greek mathematician, Eratosthenes, measured the size of our Earth with a great degree of accuracy. It was known that at a certain time in Syene, Egypt, the sun was directly overhead at 90 degrees. We'll call that point S. At exactly the same time in Alexandria, straight north of Syene, at point A, the position of the sun was measured to be 82.8 degrees away from the horizontal. That difference, 7.2 degrees, is the measurement of angle A. Because the sun is so far away, we can draw the 2 lines extending from each city to the sun as parallel lines. Since angle A and angle C are corresponding angles of 2 parallel lines, they're equal. That means angle C is also 7.2 degrees, or 1/50th of a circle. The distance AS from Alexandria to Syene, then, is also 1/50th of the complete circle of the Earth. This distance was measured in Eratosthenes' time in units called stades. It was 5,000 stades, making the circumference of the Earth 5,000 times 50, or 250,000 stades. No one really knows the exact equivalent of a stade, but Pliny estimated it was about 157.5 meters. Using his value, we multiply 157.5 times 250,000, which equals 39,375 kilometers. Since the true circumference of the Earth is about 40,000 kilometers, we see that Eratosthenes' calculation was amazingly accurate and important, because once the shape and size of the Earth were determined, the distances of heavenly bodies could be measured by trigonometric methods. By using parallel lines, Eratosthenes was able to make a remarkably difficult measurement, the circumference of the Earth. Many other Greek geometers, including Euclid, incorporated the notion of parallel lines in their conception of geometry. Euclid stated several postulates as truths that were to be accepted as self-evident. For example, 2 points determine a line. A line can always be extended. A circle may be drawn with any center and with any radius. And all right angles are equal. So far, so good. But the fifth postulate didn't seem quite as self-evident as the others. It states that if L is any line and P is any point not on the line, then there's one and only one line through that point P that doesn't intersect the line L. There's evidence that Euclid himself was uncomfortable with the parallel postulate. Euclid and many other mathematicians went through a long series of unsuccessful attempts to prove the parallel postulate on the basis of the other postulates. After 2,000 years had passed, mathematicians began to investigate the consequences of negating the parallel postulate. Thus, the non-Euclidean geometries were born. In elliptic geometry, Euclid's parallel postulate is replaced with this one: there are no parallel lines. To help us understand elliptic geometry, we'll apply it to a sphere, like our Earth. Say you wanted to make a basic measurement on a sphere, the shortest distance between 2 points. Let's pick 2 points, New York and Tokyo. You know the shortest distance between 2 points on a plane surface. It's a straight line. But on a sphere, let's trace the path of a jet traveling from New York to Tokyo. First, let's look at the route as if we believed the Earth to be a flat Euclidean plane. If the jet flew a straight line route on this flat map at an average speed of 550 miles per hour, the trip would take about 18 hours, and the distance would be nearly 10,000 miles. But looking at the Earth as the surface of a sphere, the distance between 2 points is a curved path. The shortest of these paths is along the great circle route through the 2 points. A great circle is the set of points that's the intersection of the sphere and the Euclidean plane containing its center. If the same jet flew the great circle route from New York to Tokyo at the same cruising speed as before, the mileage this time would be a little over 6,000 miles, and the trip would only take 13 hours. In fact, all pilots and sea captains use great circle routes when navigating their jets or ships. When we think of our Earth as a sphere, the equator and the circle passing through the North and South poles are examples of great circles. As a matter of fact, they intersect, as do all great circles on a sphere. Thinking of the surface of this sphere as our plane, our points as points on that plane, and our lines as great circles, then we can understand that there are no parallel lines because there are no parallel great circles. In elliptic geometry, every triangle has an angle sum greater than 180 degrees. It's even possible to have a triangle with 3 right angles, clearly an impossibility in plain Euclidean geometry, where the 3 angles of a triangle must add up to 180 degrees. A completely different non-Euclidean geometry, called hyperbolic geometry, was developed by Karl Gauss of Germany, János Bolyai of Hungary, and Nikolai Lobachevsky of Russia, all of whom worked independently of each other in the 19th century. Although they all came to similar conclusions, Lobachevsky is given the lion's share of the credit. He replaced Euclid's parallel postulate with a new one, which called for more than one parallel to a given line through a point not on that line. Hyperbolic geometry may be envisioned on a surface called a pseudosphere, which looks like two infinitely long trumpets glued together. Unlike a sphere, which has positive curvature everywhere, a pseudosphere has negative curvature everywhere, so the lines bend in on themselves. On the surface of a pseudosphere, the sum of the angles in any triangle is always less than 180 degrees. Alternative geometries were developed not to provide theories about unusual surfaces like the pseudosphere, but to show that from assumptions other than Euclid's, equally consistent geometries could be deduced. Thus, mathematicians became free to explore entirely new theoretical worlds. But this is a show about practical applications. So, in your everyday life, unless you're flying a plane or sailing a boat for long distances, you can assume that the shortest distance between 2 points is a straight line, like this. Must be the curvature of the Earth interfering.